Hi, everybody. Good morning. Good to be back here at Embedded World doing our presentation. My name is Amit Kumar, the Director of Product Marketing at Cadence. Let's get started. So just a quick overview of what we are going to cover today. System designs is a complex topic. It's deep as well. We only have 30 minutes, so we'll try to cover as much as we can. We'll try to give you an overview on the automotive market trend. None of the system design is complete without talking about perception sensing. So we'll do that. We'll present you some of the use cases in an automotive and some of our products that are useful for these use cases, whether it's vision-based processing, radar, lidar, audio. We have to talk about AI because we're in a world where AI is developing fast. Then we'll give you an example of a radar processing signal chain, and then so we'll take some Q&A. So we all talk about ADAS. We all talk about autonomous driving. There is a lot of external sensing that is needed to enable a car to operate in either a semi-autonomous mode or an autonomous mode. From the top left, if you look at, there are a lot of sensors, whether it's vision-based sensing or radar-based sensing or lidars. The digital cockpit. So cockpit is becoming more important too because it ties directly into user experience, human-machine interfaces, which needs a lot of processing. So that's where a lot of our products in the audio domain comes, with Casey, my colleague, will cover. We cannot talk about automotive without functional safety. So we talk about how we can make the car or the vehicle safer by using the components that are also safety certified. And then in the bottom left, there is a new segment that's coming up pretty strongly because of some mandates from a lot of these car assessment programs, which is in-cabin sensing. So we used to have driver monitoring systems, but now we have child presence detection as well as the occupant monitoring systems. All right, so a typical block in an automotive or for the ADAS comprises of the perception layers or perception side, which is the hardware as sensors, and then you have a perception stack that is running. The state estimation is usually where the vehicle's state is or where the vehicle exactly is, which is delivered by either maps that are preloaded, which are a little bit of things of the past, but GPS-based or GNSS-based location is what tells where the estimate of the state is, of the car is. And then there's a lot of planning and prediction that goes on in a vehicle to get you to the destination, and for that, control is needed. So if you look at these four blocks, we are going to talk a little bit more about how the processing takes place in these four blocks. So from the top, on the perception sensors, we have a lot of cameras, whether it's a monocular stream, whether it's a stereo stream. We have radars, short-range radar, mid-range radars, long-range radars. We have lidars. And very recently, we have started getting more traction on the thermal sensing or the thermal imaging because optical needs some kind of compensation, especially in the conditions where the car has a difficulty to see. So nighttime driving is where thermal sensing can be extremely helpful. So those are all the blocks for where you need processing power. And since the number of sensors are growing, so is the compute requirement. So the radar sensors, the vision sensors, the lidars, and the thermal all needs to be processed efficiently and in as low power budget as possible. So that is the topmost portion. The mid-level function is mostly your data processing and your fusion. So whether you do object localization or classification, you do the lane detection, localization and mapping, or the estimation for the trajectory. That's where you need planning and prediction algorithms. And then the high-level intelligence to make the assistance systems work is where it comes as planning and control. So whether it's a reactive layer, like say braking or adaptive cruise control, lane changes, or it determines some kind of a path planning or some awareness of in regards to where the vehicle is contextually. And finally, the decision making by the ECUs and certain actions for which the ECUs are programmed are all done in this block. So this was all what happens under the hood. And this is how Cadence Tensilica Group, which me and Casey represents, the product that are working under the hood. So from extreme left, we have dedicated DSP cores that are targeted for various applications, whether it is audio, whether it is radar lidar processing, whether it is vision processing, whether you have a dedicated need to process floating point operations, and then we have dedicated cores for AI. So if you look across the previous chart, none of those functions are possible without the efficient processors that are needed into a system design. And that's what we do. All of our DSP cores are built on a 32-bit RISC processor. And for details, I'll be happy to talk to you in our booth. So if I have to map the first slide of how we enable these things, so we have solutions for all the steps, whether it is a perception sensing, whether it is a state estimation, whether it is a planning and prediction, and planning and control. So we have solutions that we can map it, and we are very successful in this. A lot of customers already use us, and we'd like to talk to you more. If you have questions, we are here in Hall 4, booth 4219. The smart cabin, though today it is not directly tied into the active safety, but at some point of time, it will get tied into active safety, because if we know the driving state of a driver, and if the car or the vehicle has a preemptive decision-making capability, it can prevent the accidents and make the car more safer. But today, we deploy mostly vision systems for driver monitoring systems, but as we see, there are multiple sensing modalities that are coming in that are deployed inside the cabin. So for example, we need to detect and classify certain objects, and these are not necessarily humans. What kind of activity is taking place? If we have a way to classify that, that'll be pretty good. Presence detection, which is actually a mandate by Euro NCAP now to detect child. Footwell detection, there are a lot of times when things slip in the footwell. So if there is a way to detect that, body and pose estimation, pose tracking, intrusion detection, and then the live vehicle view. So driver monitoring system is mostly on the vision side, and I think we know how the eye tracking works, how the gaze tracking works, and how the distraction monitoring works. But another important point, function or a use case is the vital signs. And if we are able to measure the micro Doppler activity of a person who's driving the car, I think that gives a great advantage to bring safety to the vehicle. So that's where your heart rate monitoring and your breath rate monitoring and the pulse rate and the oxygen levels come in. If I look at various type of sensors that are needed for this, it's either vision plus radar. Off late, we are seeing time of flight that is entering into this segment. And from Cadence perspective, if I give you kind of like a high level system block, fully mapped against a lot of data sources like your sensing, a lot of pre-processing whether it's a noise reduction, pyramid scaling, FFTs, color conversion, or AI inferencing. We have steps that we can follow in a system on chip design, and we can provide those kind of solutions that can make sure that these kind of algorithms are processed perfectly. So this is my last slide before I give it to Casey. But we have a lot of success stories that we can openly share. These are some of the bigger names of the system on chip companies that we have successfully worked with. And there are a lot of projects that are still undisclosed, and we may be able to share at some point of time, but not today. So we're a successful company with a successful tool chain, nice IDEs, and success stories that you see here. And I think with that, I will introduce to my colleague, Casey, who will take you through the infotainment segment.
Hi, my name is Casey Ng. I'm the Product Marketing Director for Audio. So in cars today, infotainment is becoming a very important sector. Particularly, cars are fighting with each other to try to provide better audio systems, because the audio systems is highly visible and customers can feel it, while the ADAS might be hidden under the hood and they don't see it, right? So if you are spending the type of money for a new car, you want to find out how many speakers you have, whether you have a Dolby Atmos, etc., right? So it's very obvious manufacturers are investing a lot to elevate the audio experience and all the infotainment features. So why do we have to implement a DSP core in the modern SoC that's used for infotainment? Because the main reason is that DSP cores can effectively and efficiently perform computationally intensive real-time audio processing. For example, like filtering, removing noise, encoding and decoding, like playing back MP3 or playing back Dolby Atmos. And in addition to like decoding the Atmos content, which is like multi-channel, you also have to render in a car, and some advanced algorithms in the car, for example, they are trying to cancel out the nodal effect to make the car entertainment more effective. So another reason is that you still need to be aware of the power efficiency, because the cars are heavily electrified, right? So we also need to be concerned with power efficiency, although not as critical as a TWS earphones. We still need to be aware of the power. Now, by offloading the audio signal processing to the hardware, we can improve the system performance and reduce also the latency. If you are doing in-car communications, the latency could be very annoying if you have to wait a moment for the sound to come back, right? So having a DSP with real-time processing, we drastically reduce the latency, particularly when we have to do heavy processing. And that's why we are seeing the new SoCs with multiple high-end DSPs internally. Now, last but not least, the Cadence DSP has the widest ecosystem support. Today, we directly provide over 200 codecs, and we have more than 200 ecosystem third-party partners that operate and provides audio software on the Cadence platform. So this is an example of a modern SoC with a Hi-Fi DSP core. You can see the red color is the DSP, and today we can see anywhere from one DSP to multiple DSPs. In many cases, the current production models could have up to 3 or 4 DSP cores. So what is it used? In today's car, we are already seeing for example, the cabin voice communications. When you're talking through your phone with the Bluetooth, we are using voice communications, and hidden from your perception is that there's a very advanced noise processing. They're trying to cancel out the wind noise, the road noise, the echo. And many of these algorithms today are also AI-based, so they are more effective. Unaware to most customers, for EVs, we also have engine sound enhancements. Like, for example, the E-Mustang has we call it a fake engine noise, so that you can feel the speed, but actually is some DSP algorithms outputting sound through the speakers to provide the sensation of acceleration. Obviously, immersive sound, everybody knows, particularly in China, many of the EVs in China are fully equipped with multiple speakers. There are high-end cars with 60 or 70 speakers with the immersive audio decoding Dolby Atmos. We also have other advanced use cases like the road noise reduction. So we can process in real time the noise from the roads and the vibration, and then we try to cancel it out using the speaker and other acoustic devices. So in today's car, why are we implementing a DSP? So if we look at how the car stereo system are deployed with particularly a lot of speakers and microphones, if we have a traditional DSP that is in a distributed systems, if we see, we have a challenge because in all the modern noise cancellation applications, if we have to bring the microphone input back to the head unit, and the audio subsystem has a separate DSP providing processing power for multiple speakers, we have a latency issue. So we see the trend is to improve the performance by having multiple DSPs in the main SoCs. So by having multiple hi-fi cores in the main SoC, we can reduce the latency and bring all the processing power to the head unit. So this is one way of reducing the cost of the infotainment systems. So if we compare back, this is a fairly sophisticated system, and we are distributing 3 DSPs in a 24-speaker system, for example. But if we put 3 DSPs into the main SoCs, then we do not have to distribute the system, and we also reduce the latency. So Tensilica Hi Fi IP is in today's many of the infotainment SoCs. As we mentioned before, we have a very wide support for multiple codecs. We have over 200 codecs ready to go, and we have more than 200 ecosystem partners. Also, we support all the digital radio standards, and it's very important for the cars. If you know what's happening, 10 years ago, or more than 10 years ago, we were the first DSP in the NXP's digital FM radio, doing the FM radio decoding. So it started from a long time ago. We are in the infotainment. And today, we move from FM radio to the whole Dolby, DTS, and Audio Vivid is a new immersive audio standard that is in China. So so this goes back to the first infotainment chip in 2012. That's the first Hi-Fi core, Hi-Fi 2 in the NXP chip. Now we are seeing that today we are heavily moving from traditional classic DSP algorithms to AI-based algorithms. The AI models, they are learning from real-world data, and they can adapt dynamically. But classic DSP algorithms, they are relying on fixed rules. So AI can be fine-tuned for specific scenarios, and classic DSP, they do not have such a flexibility. So the AI use cases can also handle extreme and marginal noise patterns. So AI generalizes well across different environments and is very robust against different noise characteristics. So that's why AI-based audio processing is becoming dominating in today's vehicle and infotainment systems. So to condense it, like in the in-car communications, we have the voice input processing. So in these cases, we need to do noise suppression to suppress the road wind noise and do echo cancellation, and also doing beamforming to focus the speech to the drivers or the passengers. And we also see cars are enhanced with the smart AI agent, so you can speak to the car, you can directly ask the car to turn on the air conditioners or turn down the heaters, etc. And for more advanced automotive applications, we have zone audio and audio bubble. So the drivers and passenger, they can all communicate with different persons at the same time without interfering with each other. And for the immersive audio, cockpit audio, obviously, we have all the software decoding for FM radio, HD radio, DAB, and we can decode MP3, AAC, all the advanced formats, like the Dolby Car Experience, which is Dolby Atmos for the car. And further after you decode the Dolby Atmos, we have partners that are providing algorithms like the Direct and Alchemist, where they are doing further processing to enhance the listening experience. And to the more advanced use case, they are not so popular today, but is coming very fast, would be like the active noise cancellation for the road noise. These are like the ANC headphones, but in a car, you're trying to cancel out the road noise and the wind noise using speaker and active monitoring. Acoustic event detection is another safety features, like it will detect for glass breakage or any incidental noise like a sirens or police sirens. You can create warning signs for the driver. And also, so we talk about engine sound enhancement, that we are generating fake engine sound for the EVs. Actually, not just for the EVs, but for some advanced high-end cars like Porsche, the speakers are actually pumping back the fake engine noise back into the cabin to create a sensation of speed. So we have partners that are doing that type of stuff for our customers, for the actual OEM car manufacturers. The AVAS alert today, where it's very simple, it might just beep when it detects a pedestrian. But when we combine AVAS with immersive audio, in the future, we can have directional cues. Like you can actually hear where the passenger is from because the speakers can output exactly a directional cues, and you can hear the warning sound coming from the left, the right, or the back. As I mentioned, so these are all our automotive partners, just some of them, but not all. So just the select ones that you might recognize some of these partners. So this is the summary. So you want to conclude?
Thank you, Casey. So I think in summary, I think Casey walked you through some of the audio use cases. I walked you through some of the video, vision, and other perception sensing use cases. In summary, the key takeaway that we want to give today is, Tensilica Group in Cadence has been working with automotive customers for a long time. Our latest products, whether it's the Vision series that you see on the top, or our dedicated accelerators that are the new product basically for the growing 4D imaging radar type of use cases, or the NPUs that we call NEO, which is an AI accelerator today in the chipsets, or the Tensilica's Hi Fi audio cores that Casey just walked you through. All of them are available, and we'd like to show you more demonstration at our booth, which is in Hall 4. And we do support a very rich ecosystem partners, so which can help you do your design, do your algorithms, and implement on your system accordingly. And that's it. Please visit our website, and thank you very much. Appreciate it.